Okay, guys? So today is still an introduction. It's usually the first lecture that I deliver, but I try to flavor it with something else. So the first thing is, what is the limit? What's the idea behind it? And you might actually not guess it, but what is the weirdest number? The number that took longest to adjust to? Well, aside from complex numbers, it was 0. And one thing about it is, well, think about prehistoric times. So you go and you have to hunt. You're a hunter-gatherer. Now you bring a bunch of buffalo to your wife. Wonderful, she's happy, right? You brought 5 buffalo to your wife. But what do you do when you could not find any buffalo? What are you going to tell your wife? So eventually a very smart person figured he can say to her that he brought 0 buffalo. And 0 is not nothing. Okay, so you would actually find yourself often making the mistake of saying 0 is nothing. It's not exactly so. So what is 0? First of all, 0 is the additive identity. In other words, 0 plus any other number, whichever numbers are. It's a huge discussion to understand what numbers are. But 0 plus any other number, or 0 itself, will be that other number. That's known as additive identity. Now from there, we can easily prove that 0 times another number has to be 0. You see, you have to think about it, right? Let's see, before I proceed with the proof, I was pretty tired in the morning. I haven't asked them, but what about you guys? You are evening birds. So tell me, please, what do you think? Why is 0 times x always 0? You can type or speak to me. Well, so thank you so much, Pavel, for saying anytime times 0 is 0. But are you dogmatic? Somebody told you that, or you have reason for it? Nothing multiplied by something is nothing. But what is it to multiply nothing by something, you little philosopher? Carolina.
Because it's like, if you want to know, like if you have 0 batches of 2, you still have 0 batches of 2.
So you mean you have no batches and that's 0? Well, that's not terrible. Let me show you how this is answered mathematically. Okay, mathematically, because we have to be absolutely sure that we are not mistaken by what we are saying, right? I can show you examples. Maybe I will do that later, where your intuition is going to be incorrect. I already did it on the first lecture, right? So here is how you can do it, what you call in abstract algebra. So we have 0 times x, it's the same as 0 plus 0, right? 0 can be written as 0 plus 0. And provided we have this foiling method, so I can multiply x into the parentheses, I have 0 times x plus 0 times x. And so I'm not going through all the rigor, but you can then cancel it out, right? You have 0 times x, it's a number. A number minus itself is 0. So we have 0 equals to 0 times x minus 0 times x, which means that 0 equals to 0 times x. So I'm not sure if it's satisfactory to you. I haven't gone through all the justification of what's a field, of what are numbers, but that's what you do when you go higher up. Okay, so this is just a very brisk explanation of why 0 times anything is 0, without intuition, without philosophy, but just by algebra. Now, next is a slightly harder question, maybe more interesting question. Why can't I divide by 0?
Because there's nothing that you can divide. Dividing by 0 means like you can't divide by anything. It's just not possible.
Well, you have to be careful, right? You see, it's very hard to come up with a good explanation on the spot, right? You were taught this in school all the time, and most likely you have not spent much time thinking about it.
I think it's if you try to divide anything by 0, you're just not gonna make any progress. Like you try to divide by
But why?
1.
Why are we not going to make progress, Pavel?
For example, if you try to divide by 1, you can keep subtracting 1 until you get something. But if you see how many times that like 0 fits into even 0 or like any other number, it's going to be an infinite amount of times because you're not going to subtract anything.
How many times? Well, we say when we divide, so all of those explanations are somewhat dangerous because who knows what can happen. Here is how we can justify it, right? We know that 0 times anything else is 0. Assuming we know that, and I try to give you an algebra there, right? Let's try to understand what is, let's say, the nature of the number 1 over 5. Nature of the number 1 over 5 is such that if I multiply it by 5, I get 1. Yes? 5 times 1 over 5 is 1. Now, if 1 over 0 is something that exists, then this number multiplied by 0 should give me 1. Do you agree? That's what 1 over 0 is. The fraction, it's just a language thing, right? It means this is an element that when you multiply by the number below it, you get 1. So 1 over 0 times 0 would have been 1. But 1 over 0, if it is a number, times 0 has to be 0. We already proved that 0 times anything is 0. And so if I claim that such a number exists, then 0 times 1 over 0 is at the same time both 1 and 0, and 1 does not equal 0. Okay, so that's a way to say that there would be a contradiction. That's just by using pure algebra. Okay, so let me know, guys, if you have any questions or objections or anything in my explanation so far hasn't been clear. You follow, right? So if I prove that 0 times anything is 0, and then if 1 over 0 is anything, then by the definition of this expression, it has to multiply 0 to 1, but nothing can multiply 0 to 1 because anything times 0 is 0. That's roughly how I try to describe it. But you see, what if you really need to divide, desperately need to divide by 0? And that's the next illustration. It happens all the time. So let's try this game. Suppose that you are working somewhere in court, or you are, what's it called, CSI, right? So you are trying to investigate what did this culprit do? Is this culprit, when he drove past the traffic light, how fast did he move? All you have is this video recording of a car moving on a straight line on the x-axis, okay? And you see what you can do. You can see that the position of the car on the x-axis is a function of time because you can select the time on the time bar. And once you select it, so for example, if you put the time bar at 0, the car is at 1. If you select the time bar at 2, the car is at position 5. So the car is in exactly one position in space for every given moment of time. So suppose that you play with this video and you realize the following pattern. So you see that at 0, the car is in position 1 on the x-axis. At 1 second in the video, the car is in position 2 on the x-axis. At t equal to 2, the car is in position 5. At t equal to 3, the car is in position 10. Could you try to predict or guess what might be the position of the car at time t? What's the function? What's the formula for x of t in terms of t? There's a student, guys, that's trying to figure out with this classroom. I will just try to text her the code. So my question, guys, here is what I want to know from you. what is the position as a function of time, right? So you have this data and you're trying to figure out what might be for a general t. Well, some person actually I see has a wonderful name for mathematics, Factor. That's a great name for mathematics. Last name Factor. All right, so we have a bunch of answers, good, except not, it's t squared plus 1. The correct answer is t squared plus 1. Give me 1 second, guys. Apologies, guys. Okay, back to our thing. So the formula, you can just see t squared plus 1 at least works. That definitely, this information is not sufficient. I'm just checking if you can figure out what's the function. Notice 0 squared plus 1 is 1, 1 squared plus 1 is 2, 2 squared plus 1 is 5, 3 squared plus 1 is 10, right? So definitely this formula matches the data we have observed here. Now, let's try to understand what we have to find. So you understand that the car has passed a traffic light. Maybe it passed the traffic light on red, or maybe, let's say, the speed limit. What's the speed limit in New York? The speed limit in New York when there is no sign is 25 miles an hour, right? Why do you think that's the speed limit? Because the government does not have enough money, right? So they need to tax you. So what is it that we need to find? Let's see if anybody can tell me what is it that we need to find. We want to know with what speed or with what velocity the car has moved past this index 5. So it actually passes the position 5 when time is 2 seconds. Okay, so let's say those are measured, the distance is measured in meters. So let's say the car, when we begin the video, the car is at 1 meter away from the origin. And 2 seconds later, the car passes the traffic light. We want to know with what speed it passes the traffic light. How many meters a second, let's say. And so what exactly is that we are searching? What is velocity?
Velocity equals meters per second.
Well, I want like a very, very careful explanation of what is this velocity, what is it measuring exactly? That you all have used this concept, but think about it. Can you explain what is velocity? So Rafid, exactly. T is time and xt is displacement or position more so, right? So it's exactly where on the x-axis the car is located. Again, right, what we have here, you see that x is the position of the car and t is time. We know that x is a function of time because if I move the time cursor anywhere, the car will be in exactly one position, right? So let's say at the beginning, the car is in this position and 2 seconds later, the car is in this position. Anywhere in between, the car will be somewhere on this axis and it will occupy, it's actually a point, to occupy exactly one point in space. So what I'm asking you guys is to think and tell me, what is it really that you speak about when you mention velocity? Distance over a period of time, Hadi, and that's very good. But what is it that we're trying to measure? So first of all, of which velocity? Rate of change, yes, but specifically, what is this concept that you are trying to capture? It's a vague question. How fast? But well, let me help you a little bit. Okay, so if you go and you run, right? You go for a jog. So some jogger is running 6 miles an hour, correct? Well, that's very, very, okay speed. Not nothing very special, nothing very terrible, right? It's just okay speed, 6 miles an hour. So how much is this jogger going to run in half an hour? So Alisa, yes, distance over time, all wonderful. Let me just ask you again about the jogger. 3 miles, somebody says. Eric Hanna says 3 miles. Okay, so everybody agrees, 3 miles? The jogger runs 6 miles an hour, so in half an hour, the jogger moves 3 miles. And how many miles will the jogger move in 2 hours? Well, it's a very good question, right? So I want to see what you answer, guys. It depends, right? So you see, when you say it depends, right? So if you say it depends, then what is it that you are trying to, what is it that you're expressing? So notice let's start with very, very, very simple motion. If you cannot describe velocity in general, start describing with the simplest instance of it. So people that answer 12 miles an hour, sorry, 12 miles per 2 hours, right? What are they really saying? They are saying really the following, that the jogger is moving at a constant speed. You agree? If the jogger is moving at a constant speed, then in half an hour, the jogger will travel 3 miles. In 2 hours, the jogger will travel 12 miles, yes? At a constant speed. Now think about it very precisely. What is it that we're trying to express here? Consistency we're trying to express as follows. So if you take a given interval of time, any interval of time, anywhere, during the morning or day or night, no matter. If it's the same interval of time, there is going to be the same amount of displacement happening per that interval of time, right? That's what you do. You compare two quantities. Neither time nor space are easy to understand. You only have some intuitive understanding of it, but the idea of uniformity is that things are monotonous, right? When somebody runs at a constant speed, it's monotonous. In other words, there is no change from one interval to another. Every 2 interval segments of time look the same. You are seeing the same particle moving exactly the same way, if you can trace it. Do you agree? Guys, you see, velocity is something terribly difficult, right? If it were so simple, you would all know the theory of relativity, right? And that's very weird. So let's see if you understand the very, very beginnings of it. So if something is moving at a constant speed, then what I try to communicate, it's very similar, by the way, to what we did with the patients, right? So I remember when we were measuring whether the infection is spreading or not, instead of using time, we were using the number of people tested, right? So if you take the number of sick people and divide by the number of people tested, and that's the same, that means the infection is progressing linearly, right? It's exactly the same situation over each interval of time. There is no spread. It's not increasing massively. It's not bigger than it used to be, right? Similarly here, where you're trying to communicate monotony. So this is where we begin. If we move with uniform motion, then we can communicate it by one number, right? If you just say 6 or 12 distance, right, you are not normalizing. That means, you see, you're trying to say that if you're trying to express the idea that every interval of time, no matter how big or how small, carries the same displacement in position. Now, if you understood the explanation, guys, please respond and write to me that you understood. Okay, write yes or something, or ask me questions. Don't be shy. Okay, you understand what I divide? So it's one number there, right? And the idea is with one number to communicate that if I have interval this wide, the displacement will be proportional to the size of the interval. If it's smaller, exactly the same situation. Good? So you understand, my point is, guys, it should not be arbitrary. Do you understand why to compute velocity, what I do is I take 2 moments of time and I take change of position, or that is the distance traveled over this time, divided by the difference in time, okay?
So you're saying velocity is more of like a rate?
Well, sure, rate, but rate is also just words, right? What you have to try to picture, forget about words, right? What I picture when I think of velocity, I picture time. Whether time is this short or this wide, I picture that what's happening is monotonous, right? Same motion. I don't see any difference, right, over this time. Or if I take 2 intervals of exactly the same size here or here, I don't see any difference in phenomenon between those 2 intervals of time. Good? So constant rate of change, it's velocity. You can say constant velocity is a constant rate of change, or so in particular, let's try to find the velocity. We need, again, guys, right? We need something that's possibly for you is obscure. We'll try to make it more precise in a moment. We want to figure out how fast is this car moving when it is here, when it's by the traffic light, okay? Okay, so we are definitely interested in the time when it's by the traffic light, and that time corresponds to 2 seconds, right? So we can try to take two moments of time. So we have 0, I just chose 0, and I have 2, right? So I can take the displacement. How much displacement happened during this interval of time? So I have x of 2 minus x of 0 divided by 2 minus 0, which gives me what? X of 2 is 5, x of 0 is 1, right? You remember the formula. It's t squared plus 1. So at 2 it's 5, at 0 it's 1. So we have 5 minus 1 over 2. And I calculated this number too. So if time is in seconds and distance is in meters, so that's 2 meters per second, okay? But the problem with this situation is, look at it, right? With the runner, I can take any interval of time, and if I take displacement over that interval of time, I get the same number. You see? 6 over 1, 3 over 1/2, 12 over 2, I always get the same number. But here, I take different increments of time, and I obtain a different number altogether, right? So if I take 1 and 2, 1 second and 2 seconds, so the distance is now 5 minus 2. 2 minus 1 is the difference in time. Now I see 3. You see, 2 and 3 are not the same value. So what does it say about the car?
Doesn't move at constant rate.
It definitely doesn't move at a constant rate. Do you realize, guys? See, it seems possibly trivial to you, but I'm not sure. Either you're completely confused or you think you are not confused, in my opinion, right? I don't think there is a third possibility. Either you are confused entirely, or you think you understand and you don't realize that you are confused. Again, you see that what we have with constant velocity, the idea is that if I take any increment of time of the same size, that's called normalization, right? Then I should see the same displacement in that increment of time, okay? And if I change the increment of time, if I make it smaller, I might have smaller displacement, but the ratio stays the same. That's the idea of the ratio. The ratio is just how much unit of time is getting displacement, right? That's what you communicate. In 1 unit of time, when you say you run 6 miles an hour, you're saying 1 unit of time in hours takes 6 miles, right? And that's what you're describing, right? And therefore, of course, half unit of time will take half the amount. A third unit of time will take a third the amount. That's why the ratio is always the same. Make sense? But you are really thinking it's very similar to if you have 12 apples and you have 2 children, each child takes exactly 6 apples. Half a child takes exactly 3 apples, because if each half of the child receives the 3 apples to make 6 for the entire child, okay? But here, clearly we don't have this situation. We have the number 3, and here we have the number 2. So now this whatever it is that we're trying to find is not a constant motion, right? We're not dealing here with constant motion, and yet your daily experience tells you that there is such a thing as velocity. There is such a thing as speed. Many of you have licenses, many of you drive cars, many of you have been in cars. So here are the questions that I'm trying to ask. Does the car have velocity? Well, does the car have velocity, guys?
Yes.
I want to see what you write to me. So write yes if you think the car has velocity, please. Now I'm going to ask you a confusing question. You're saying car has velocity, and I come to you and I'm asking you, what does the car have? Right? What is it that the car has? Right? So let's say if you say there is an elephant in the car, a car has an elephant, you can describe it, right? You would not just say elephant, right? You would say, oh, it's this gray animal that might look like if you've seen a mouse, and it has a long nose, and it's very large and heavy. You can describe it, right? So the question is, what does the car have? You say it has velocity. What does it have? And how do you know it has it? That's a very important question. Another part of this question to bunch it all together, if I pause the video, now I pause the video at 2 seconds. It's paused, right? It's not moving on my screen. Just like, as you can see, it's not moving on the screen, it's paused. When I press pause, does the car have velocity, or when I pressed pause, it stopped having it?
On the screen, if it's a recording, it stops.
Well, you don't see the car move, but does the car, in some sense, continue to have velocity? Or if you're saying in law, can you argue somebody filmed somebody speeding past the traffic light, and then you can argue, oh, you press pause, and you can see when you press pause, then nothing moved. Therefore, I was not speeding. Right? You don't accept such. You don't accept this in a court of law. Why?
It still has velocity, but it's just not moving because no time's passing when you pause it.
So you're saying it has velocity. What does it have? You're saying it has velocity, but what is it that the car has?
Movement. It's traveling a distance at a speed.
How do you know it has velocity, right? So the question is, some questions, guys, they are so fundamental that you cannot necessarily give an adequate conceptual explanation of them, but you can perhaps describe the operational definition. How do you know? Operational definition means how do you measure it, right? If you can measure something, then you know it has it, right? You don't necessarily, so when you speak about a force, it's very difficult to describe a force, but you can make some precise definitions by which you can measure it, right? So you might say a force is what's measured. Similarly, time is considered to be that which clocks measure, right? So whatever a clock is.
So you're saying that because we could measure a velocity exists.
Yes, that's an operational definition of it, right? Operational means whatever you can measure, whatever you can compute is something that exists. So what is it that I measure? How do I know? Very simple question, actually, right? How do you know that this car has velocity? What is that when you say velocity, so that it's not very complicated, it is what specifically?
Moving.
Well, have you driven cars, guys? Have you seen the dashboard? How do you know if you are traveling past the speed limit?
Speedometer.
The speedometer.
The speedometer. So what the car has, it has a speedometer. And the speedometer is showing a number, correct? So if you're seeing the car from the outside, but if you had a camera inside of the car, you could have been reading. So if you had a video, simultaneous video recording the speedometer of the car, then you could just juxtapose the videos, and you could just, at the moment when you pause, you can see the speedometer. You can see the dial, and you say, aha, at this moment, the car was moving whatever the speedometer is showing. You understand? So when I'm trying to figure out what's the velocity of this car, I'm trying to recover the velocity displayed on the speedometer. Okay. So what I'm trying when I'm asking for instantaneous velocity, when I'm asking you what is the velocity of the car at time t equal to 2, at the time when it passed the traffic light, I'm asking you to figure out what was the, to figure out somehow and explain your reasoning to figure out what was the dashboard speedometer displaying. Does it make sense? So you in this video don't have the evidence, right? It's like inference, right? So you see CSI, you might see somebody coming in into some house, then you hear screams, and then you see this person moving out with some big bags, and you think it must be robbery or something, right? How do you make the inference? You have not witnessed it. So similarly here, you need to make inference by which you could tell me what was the speedometer showing at t equal to 2, at the moment when the car passed the traffic light.
So I'm guessing the question is no, because of the fact that we can't really measure the velocity because we don't know how fast is the car going. But since we have the period of time, right? We know from it started from 0, and when it hit the when it hits the what's the word, the red light, we know that it's 2. So is that why? I hope I'm saying it not like weirdly.
No, it's and thank you, by the way, for talking. I really appreciate it tremendously. So first, a few clarifications, right? So what do we know? We pretend, I mean, here I just gave you some values, but let's say we know the position of the cars, sorry, at any given moment of time. So we know the car as a position function of time. So whenever I specify a moment of time, I know exactly where the car is located. Is this clear? So for example, at 0, the car is at 1, because 0 squared plus 1 is the formula by which I relate position to time. And if it's in position, if time is displaying 2, then 2 squared plus 1, which is 5. The car is here at the red light. Okay. Good. So the question is, here's what we, I hope, established, right? To make it very simple, when I ask what's the velocity at t equal to 2, I'm asking what did the dashboard display at 2 seconds into the video. Make sense? You're trying to figure out, based on this information, you know where the car is. You can see it move, right? You just don't have a view to the dashboard. You want to know what is the dashboard displaying. Any ideas, guys? So imagine that was a task you had to figure out. What would you have done? You can play around with the video. You can know exactly where the car is at any given moment of time. From this, because we have the formula, right? So from there, I want you to infer what must have been the velocity.
What is it that we're trying to figure out?
What is the speedometer showing exactly 2 seconds into the video? So at this moment, the car is here. At 2 seconds, the car is at position 5. What is the speedometer showing? Can you figure that out? Or not necessarily, you don't have to finish it. Just tell me, what should you try doing? Alex, I think you said if it's 3. No, it's not 3. Don't necessarily give me a number, just maybe suggest what strategy to use.
Wouldn't the speedometer use 2 points, 2 locations, and then use that use those two locations, and then give it the amount of time taken to complete, you know, distance A, let's say, and then distance B,
Right.
and then do a do like, let's say, what was it, xt, like xt2 minus xt1 over t2 minus t1,
Right.
and then it will give the display there.
Well, kind of, right? So
You could graph it and look at the slope when it's at wherever the point is.
you can graph, sure, but if you want to, yes, you can graph. You don't need to graph, right? You can just calculate. Let me show you. Let's think. You see, some of those things, it's what's called philosophy in some sense, because you are trying to figure out what is it that you need to do. So, right, if we are traveling at a constant speed, all you need is 2 moments of time, because then you have an interval of time, and for that interval of time, we need to measure displacement. But here the problem is we figured out this car doesn't appear to be moving at a constant rate. Okay, so what can we do there? So you might know that velocity changes in time. You experience that, right? It always takes some amount of time, maybe very little, but some amount of time for things to happen, right? So velocity does not jump from one value to another. It changes gradually, correct? So then we might try to do this. We might try not to give any amount of time to change. So we take 2 points to be the same point, because then we are not giving any amount of time to elapse. And then if no amount of time elapsed, the velocity will have to be constant. But the problem is, so I might try to take the points 2 and 2, okay? 2 and 2, and because that's the same point, I need 2 points to calculate velocity. That seems nice, but then I get 0 divided by 0. You see, I'm trying to push this idea that in some ways you need to divide by 0 to figure out this velocity. Okay, do you follow what I'm saying? Because if you allow, if the velocity is not constant, yes, Alexei, please talk.
Did you find like the closest velocity to it, to like really close it?
That's possibly the next strategy, right? So first idea is this, right? If velocity is not constant, then we think that as soon as you give some time, the motion, the rate at which somebody is moving is going to change. So if you don't give any time, it's 0 over 0, wonderful. Okay, but that's not useful to us, okay? Because 0 over 0, we cannot divide. Guys, again, don't be too worried, right? This is not my, by no means, final explanation. This is just a flavoring. I call it a pseudo-historical account. Because, I mean, you see, if you try to read Newton, it's a very, very challenging book, right? People that first discovered and developed calculus, their explanations or procedures would be procedures that only after extreme amount of effort and by very, very smart people, it's possible to understand. But things are simplified in a way that by now many, many more people can understand. But if you try to read Newton's Principia Mathematica, it would be a very challenging read. Right, and so here is the idea in essence that people came up with, right? So I cannot do this calculation because I divide by 0. You agree? I cannot divide by 0. So the idea would be, what if I plug a fake 2? You see, I need to plug the same time, but to get away with the problem of dividing by 0, I'm going to plug what I call fake 2, and I put it as 2 hat. Let's see what happens if I do that. You understand why I put a fake 2? Because in essence, I want to measure the displacement from the time to itself. I don't want to give any amount of time, because if there is a positive amount of time, there would be a change in velocity, right? It would not be a constant velocity. But if I gave no change in time, then the speedometer could not have moved. Okay, guys, are you still more or less with me? You follow me? Right, yes or no? And if you're absolutely confused, again, don't worry. That's not our explanation. That's still flavoring. It's still what you call introduction. If you come out today understanding nothing at all, you are still in the game. Well, Carolina, so variable, we can do it with a variable, and that we will do it later. I'm going to introduce limits, right? I'm just giving you like pseudo-historical way in which this was calculated. Okay. So I carry out this calculation. Look at it. X of 2 hat, it's 2 hat squared plus 1. X of 2 is 2 squared plus 1. Right? I don't simplify them. This you can say is 5. Don't simplify. That's a huge mistake. Just look at the algebra. Okay. You see this? 1 and 1 can cross out, and then I see the following. I have 2 hat squared minus 2 squared, 2 hat minus 2. And the difference is, at least logically, this is not a real 0. Okay, look at it, right? It's by no means, guys, by no means this is an explanation. This is just somewhat how this thing developed, okay? And then this is equal to what? This is a difference of squares. Do you remember difference of squares? So a squared minus b squared is a minus b times a plus b. So what I have here is 2 hat minus 2 times 2 hat plus 2. And whoop, I can cross this out because this is not a 0, right? This is something in the number divided by itself other than 0. When I cross it out, it's just 1. So the answer is 2 hat plus 2. And then I say, well, what is 2 hat? 2 hat is a fake 2, but it's really essentially 2. So I have 4. So my prediction doing this calculation is that the speedometer is showing, let's say, 4 meters per second. Are you with me? Would anybody like to go over the explanation or try to tell me what is it that I did? How did I come up with those formulas? Why did I come up with those formulas? You see, what I hope you would learn is that you come up with formulas once you have an understanding of something. The formulas flow out naturally. They are just expressions of what you figured out. So let's begin there, guys. Write yes if you understood what is it that I tried to figure out. Okay, many of you, here is the problem. So many people start calculating something, but they have no idea what is it that they are calculating. They forget about it, right? They forget what is it that they are doing. Yes, right? So our goal was very simple. We needed to figure out what is the speedometer displaying, correct? Now, if I knew that the car was moving at a constant rate, then I could take any 2 moments of time. I don't have to worry about this specific mark of 2 seconds. 2 seconds corresponds to the traffic light. Right? That's why I made it. Correct? The arrow above 2 is just, you see, if you're good at arguments, you try to come away. You try to just wiggle your way out of a nasty situation, right? I'll get to the 2 hat in a second. It's just my symbolics. So you understand, guys, what if I knew the car was traveling at a constant speed, there is no reason to focus at 2 seconds, okay? But since I know the car is not traveling at a constant speed, or I might be worried it's not traveling at a constant speed, I need to know what's the situation at 2 seconds. So what I do is, I try to not allow any time to elapse. You understand? Because you see, if I want to have naturally a positive interval, but a positive interval will ensure that there is some amount of time elapsed, and therefore the velocity could have changed. Velocity changes with time. That's we know from experience. You agree? It never changes instantly, right? So it changes with time. So that's why I try to take the position at 2 and subtract the position at 2 and divide it by the differences in time. But that would be by 0. And so what I try to do is I try to cheat my way out of it. I say, well, let's pretend that it's a fake 2. And then we will talk about what this fake 2 is, right, in a moment. This 2 hat is a fake 2. And if I, yes, fake. In other words, it's not a 2. Because if it were a 2, I would have 0 on the denominator. But since it's a fake 2, I cross it out. And notice, I do this and there is a magic, right? I actually get 4. And maybe 4 is meaningful. And of course, you might be worried. I mean, it seems very irrational, it seems meaningless. And that's in fact, many mathematicians, many great mathematicians when calculus was created, attacked it. They thought it's absolutely not rational. It's a basically wrong type of reasoning. So let me try to tell you a little bit, just so you believe me, what is that fake 2? Yes, it's a magic. It was magic for a while until eventually, already in the 19th century, were the final stages where calculus was made very rigorous. But it took a while from the discovery. So here is what this fake 2 is, guys, right? And you could have figured it without much philosophy. Look at it. What should you do? You know that the speedometer, when you press gas or anything happens, it changes gradually, right? So if you have this video, you can move this cursor to 2 and then press play, and maybe somewhere over here is your fake 2. But this is pretty much time. It's a lot of time happening, right? So maybe your fake 2 should be close, right? So you press play, and then you see where I'm holding this red cursor, you press pause. So you have 2 and another number that's very close to 2. But even that is somewhat large somewhat large interval of time. So you might select an even smaller increment of time. The smaller the increment of time, the more assured you are that it was not enough time to change anything substantially, right? But any amount of time is still not good. So if you're a perfectionist, you select ever closer values to 2. So fake 2 is actually a dynamical condition where you select not just one approximation to 2, but many others, and you're trying to get them as close as possible to the actual 2. Do you understand? So this fake 2 is something that you barely, no matter what, you cannot distinguish it from the actual 2. No matter how you observe it, your current tools don't allow you to distinguish between this actual 2 and the fake 2, but they're not the same.
So is it like a range of decimal numbers since it's on a timeline of seconds? I guess.
So what is this 2 hat? 2 hat represents possibly 2.00001, right? So almost 2, but 2.0001, it's not necessarily good enough, right? Maybe this is still quite a lot of time that happened. Right? It seems to you that it's not for a car, but maybe for some other phenomena, it's so too much time. So many things could have changed. So you're obsessed that your fake 2 is not good enough. You understand? You're always obsessed about it. So you're always taking better and better measurements. You have numbers that strive to be 2. Okay? But in this calculation, I just crossed it out, and you get the actual answer. But that's where you have limits, okay? Where you have numbers that strive to be 2. We'll talk about limits below. All right? So I hope you kind of understand this situation. Good? So let's try to see what is the velocity at any given moment of time. Can we recover it for the entire trip? For the entire trip, it would be this, guys, you see? So if I generally want to pause the video at time t, and I want to know what is the speedometer displaying at this time, what I do is I take a fake t, which I call t hat. So it's the position at t hat minus the position at t. I can imagine t hat is slightly farther than t, right? Maybe it's a time slightly past t, but so little that I can't tell them apart, okay? So I have this. Now, what do I have at a fake t? It's fake t squared plus 1 minus t squared plus 1. I simplify and I get t hat squared minus t squared, on the bottom t hat minus t. This again is this is a difference of squares, which I can write as t hat minus t times t hat plus t, and I can cross out t hat minus t. With me? And then I end up with t hat plus t, and that is 2t. So I now have the representation of the speedometer. I know what the speedometer was displaying at any given moment of time. So 2t, what does it mean? It means that at 0, what was the speed at 0? Speedometer at 0 was what, guys? Remember, the formula is 2 times t. So at 0, what is the speedometer displaying?
0.
0. What is the speedometer displaying at 1?
2.
2. What is it displaying at 2? We already figured it's 4. At 3 seconds in the video, it will display what?
6.
6. Good? You understand what I was able to do? We will check it in one moment. You will do your own exercise.
Wait, so the speed is 2t, wherever the seconds are, that's how fast it is, times 2?
Yes, so that's what 2t means, right? So I'm able to figure out what the speedometer, I can actually construct an animation of the speedometer with the video. So I now am able to see inside of the car, even though I did not have the camera there. You see, I reconstructed that information based on the motion. I recovered velocity from position. So let's see if you can do it with this exercise, guys. You see? So a particle is moving in such a way that its position at any given moment of time is minus 4t squared plus 2. So first I want you to find the velocity function. What is the velocity at any given moment of time t, which means this is just a formula that will tell you if you pause, let's say at 5, it will tell you velocity at 5. If you paused at 7, it tells you velocity at 7. If you pause at 0, it tells you velocity at 0. And in general, pausing at t, it tells you what's the corresponding velocity. So that would be v of t. See if you can calculate. Since I don't see all your faces, I might just ask a few of you. So Ishmam Sayed, if you're here, type yes. Great. Rachel Minkovich, if you're here, type yes. Okay. Anthony Espinal, if you're here, type yes. Great. Okay.
Can we look at the other question again? I have a pretty bad memory.
Well, try without memories, right? The point
Okay.
is, you see, I forget everything completely, right? And so your names, I do not remember them. You know why? Because usually they are not Indian names, right? They don't describe your spirit. But just recently, there was a newspaper lying around, and I don't know why. It's completely coincidental, right? And there was this killer, and his name, it was basically driving in his car and killing people, killing prostitutes. And his name is Jack Underway. You understand? So, but in German, right? Jack Unterweger. So I right away remember the name because it makes sense.
Mm.
You understand? So everything in mathematics is the same way. If you remember, if you understand it, you don't forget. If it makes sense to you.
Yes.
Professor, I think I have a formula, but I'm not sure if it's like what you would
Say it
like
again.
to use. I think I discovered I have a formula. I think might be an answer.
You have a formula.
Yeah, like a function for the velocity.
Well, you're ready. So if you're ready, just type your formula for the velocity in the comments.
All right.
Thank you. When you're ready, guys, type it in the comments. Pavel, your formula well, for the velocity looks very complicated.
It looks a lot simpler on paper. I could share screens and show you,
Um,
but it is
we'll see in the
still
moment. I'll show you what I have, and then we will discuss yours.
okay.
Okay. You see, guys, when you think about it, try not to recall exactly what I said, or just try to see if you can reason it out. Would you have discovered this formula on your own? If the answer is yes, you would not forget it. I'll give you another 2 minutes, guys, and then we will go through the solution. All right. Let's try to solve this. So first of all, what is it that we're trying to figure out? Here I drew just as a particle. We have a particle. We know exactly where it will be at any given moment of time. That's what x of t suggests, right? I can move the point of time anywhere, and the particle will be in a particular position. So I want to figure out what is the speedometer for that particle. What would that speedometer show? Okay, so let's say I try to do it for some point t. I want to know what is the velocity at an arbitrary point t. What's the idea? I am not sure the particle moves at a constant rate, correct? So if I want at time t, I want to take t as one of the moments, and I want to take another moment very close to it. So for example, if t were 1, I want to take the other moment of time very close to 1. Do you agree? So this over this amount of time, the velocity might have changed. So my calculation might not be good, but in a smaller amount of time, the velocity has changed a little less. And in even smaller amount of time, it has changed even less. So the idea is, in some sense, to make t hat equal to t, but not exact, right? So it's like you're trying to make it very, very close there. So it's just like calculating your guys, first of all, do you all understand how to calculate velocity for a constantly moving particle, a constant, well, something that moves in uniform motion? Type yes if you understand. Right, what you do is change of position over change in time. And so what we do here is we pretend that the motion is constant. The motion is constant if the difference between the time of interest and the next moment of time is very small. You with me? So I press pause and I press play. So just so you can see, I press pause and then play and then pause again. And now the other time t hat is here. So this is 1 and this is my 1 hat. But this 1 hat isn't good, right? Because it's not quite a 1 hat. There is a big interval of time. So I try to be better. I press pause and play faster. So my 1 hat is better. Now I can make it even faster. And then my 1 hat is even better. The smaller the increment of time, so you hope, the less chance there has been for the velocity to not be constant, to change. You see, it requires a change. So I think, Alexei, you mentioned that regarding velocity being nearly constant. So the idea is this: velocity is not constant, but it's nearly constant if the interval of time is very small. Are you getting it, guys? Velocity in general isn't constant, but if the interval is really, really, really minuscule, then it's essentially constant. That's the idea. That's the philosophy, right? Because in your everyday experience, it took some time for anything to change, right? It takes time for everything that you observe, even for velocity. Good. So that's what we try to do here, right? So that's what this conceptually trying to do. We're kind of saying on one hand that time elapsed. On the other hand, we are trying to say it did not, so that velocity did not have to change. And we compromise by saying that t hat is really, really close to t. That's going to be limits. I'm going to explain this later more precisely, right? So in essence, you're trying to say this t hat is, why is it a counterfeit t? Because the amount of time that elapsed is so short. Yes, it's very close, it never touches. So t hat is not t, but it's very close. So that what I do here is I calculate for a constant velocity. And I claim this will be a constant velocity because the amount of time elapsed is very short. Okay, this is going to be made precise. We're going to talk in a moment about limits. This is just, this is, by the way, derivatives. So we're going to talk about it far later in the course, right? It will be maybe quite a long time since we talk about derivatives, but if you understand the idea, that's excellent. If you are confused here, you still have time. Okay, so you might even imagine that we learned nothing at all so far. So here is the calculation. Look at it. So what is x of t hat? X of t hat is minus 4t hat squared plus t. And x of t is minus 4t squared plus 2, right? So what I can do is I can cancel out the 2's and I can factor out a minus 4. If you're not terrible with algebra, right, it gets much easier later on. You can see that it's the same thing as minus 4 times t hat squared minus t squared. Let's see, guys. I want to see maybe a response. So from this line to this line, are you all good? So this is what I call algebra. So you see, I will stop and try to help you with that, but those should be effortless. Okay, such manipulations, you should be able, if you don't see them in your eyes, you should be able to move things around on the paper and reach this conclusion easily. Okay, what you do is you cancel all the 2's and you have minus 4t hat plus 4t squared. So what you do is you factor out minus 4 and you have this minus 4t hat squared minus t squared over t hat minus t. Okay. And then I cancel out the t hat. I use here difference of squares. You see, it's a difference of squares. I factor it out. I cancel, and I end up with minus 4 times t hat plus t. But t hat was very similar to t, so it's really minus 4 times 2t, which is minus 8t. My prediction is that the velocity will be just minus 8 times t, and that's what it is. Good. You understand? Again, this remark I already mentioned a few times. Good. Christian, you're okay? If you have a headache, that usually means that your brains have been rearranged and now you understand, right? I always had very strong headaches before I understood something. Linear algebra, it was so painful. One night, my head explodes, I go to sleep, next day I wake up, it's effortless. Yes, of course. Ishmael, what would you want to be explained again? Which part?
So can I ask? All right. So basically, you're saying that because it's not constant, getting it.
Because the velocity is not constant. The car is not moving in uniform motion. Yes, Carolina?
Yeah. So what you're doing is essentially you're narrowing the space.
Narrowing the time.
Narrowing the time because ideally the velocity would not have changed significantly from those.
Right, exactly. So if you give some amount of time, velocity might have changed, but unnoticeably, right? You change with unnoticeable steps, right? I get older with each second, but you don't see that I'm older from the beginning of the lecture. I look to you like I'm the same age, right? So that's because not enough time elapsed for you to notice that I get older. The same thing with every other change, right? It takes time. And some things happen very rapidly, so you need very little amount of time for the change to take place, and some things happen very slowly. In general, the slower or the rapid things, they all require some amount of time. So in theory, if the interval of time is appropriately compressed, there was not enough time for the change to take place. And over that compressed interval, the velocity is essentially the same. Ishmael, you follow this idea, right? So it's philosophy. It's not even mathematics, right? It's completely philosophy, right? Physics or whatnot, right? It begins with our philosophy. If you have very little amount of time, there was very little change. And so if there were very little change, essentially you might approximate by saying there was no change of that tiny microscopic interval of time. Okay? So I know that in a tiny microscopic interval amount of time from t to t hat, you see here is t and t hat, I can use this constant velocity trick that I did before because it was monotonous over this interval, right? From t to t hat, there was no change. So I can take difference in position divided by difference in time. And I get a formula, right? I get then it's just algebra, a bunch of algebra. The brackets are parentheses, right? It doesn't matter. Brackets, parentheses, it's just Alex, right? It's just to divide this part from that part. Okay, this is algebra, guys. When I say brackets, you see from this point to the calculation should be already something you are able to do. If not, I can help you again. But you see that's at least assumed to be the prerequisite for this course. For this class, you should be okay with algebra. If you're not okay with algebra, I'll help you guys. But stay in office hours or talk. Okay, so you simplify this thing. You have you factor out the minus 4, and then what you end up is minus 4 t hat plus t. But t hat is essentially t. There is nothing you can tell it apart with, right? It's just the same number essentially. It's not the same number. It looks to you like the same number. You understand? It's like if you press, if you move this cursor, if you move it in here, it might be almost 1. If you move it even closer to 1, you cannot tell apart whether it's 1 or not. It's just that little amount of time.
I have a question.
Go ahead.
So let's say you chose a test point and you said the test point of the time would be 2. Why not just do like 1.99 as the second point in time?
Yes, that's exactly what I would have done if I were playing with this video. You could have come up with this idea. You can take so if it's 2, you can take 1.99999 or 2.00001. You just need 2 moments of time that are not identical but are very close to one another. So 2 moments of time that are very near one another, and the reason is that you don't want to allow time to have effect, so that you want a constant velocity, and you can carry a calculation. And not this purely by algebra, by saying, oh, I chose ideally a number very close to t. You see, I am able to cancel the 0, and algebraically, I'm able to see that the answer should be minus 8t. And so at t equal to 1, what does this minus 8t mean? So for example, at t equals 0, the velocity is 0. At t equal to 1, the velocity is minus 8 times 1, which is minus 8 meters a second. If time is measured in seconds and distance in meters. So tell me, please, guys, what does the minus 8 mean? How is the car moving? In reverse or forward?
Neither.
Well, the velocity is minus 8 at 1, so it moves in which way? The reverse, exactly. So the car, in this case, it's a very primitive car. We're only in Calc 1, or this particle is very primitive. It moves on this one-dimensional number line, right? So in this case, it means it's moving back. Good. So now let's talk about limits. Okay, so what we were doing really is we were approximating a number by something that's not quite the number. It's a fake number, right? It's trying to imitate. That was the t hat, right? So what you do actually, you don't use the t hat usually. You have these 2 operations. In calculus, you have 2 operations. You have the function evaluated at a point, and you have the limit of the function as x strives to be that point. So the first idea, I think you understand. You have evaluated functions, right? Now, what is this idea of limit? Right? This idea of limit means that what I plug into the function are numbers that are C-like but never actually C. I plug a sequence of ever better improvements of C into the function, but never the actual number C. And I'm trying to guess what is happening, right? What does it look like? So I will talk about it a bit more below, but here is the difference. For example, I take a very simple function, f of x equal to 2x, okay? If I plug in minus 1, I get minus 2. Do you agree? Now, what happens if I take limit as x goes to minus 1 of f of x? So the idea here is what I do is I might construct a table. I take a bunch of test values that are approximating minus 1, but not equal to minus 1. So I might take minus 1.1. That's a fake minus 1. Yeah, it's a fake minus 1. I multiply by 2, I get minus 2.2. But that's not a very good fake minus 1, right? Here is a better fake minus 1 because it's closer to minus 1. It's less distinguishable from minus 1. Minus 1.01. I multiplied by 2 and I get minus 2.02. Not a very good fake minus 1. Here is a better one, right? Minus 1.001. I multiplied by 2, I get minus 2.002. You see what I do? And this, of course, there is no reason that this should be our absolute fake minus 1, right? There is no absolute. There is just get closer and closer, improve, get a better estimate. That's your t hat. That's your fake minus 1, right? That's your minus 1 hat. It's not really a number. It's really a process. You are with me, guys? It's a process where I'm trying to get this fake minus 1 as close as possible to minus 1. And there is no limit to how, again, limit. So it's called no limit to how close you can get. You can, for each number that's very close, you can get a number closer. Agreed? And see that's what you're saying. As x is striving to be minus 1, as you plug those inputs, you see what happens here. The outputs, again, tend to be minus 2. So then you see that limit as x goes to minus 1 of f of x is minus 2, which is f of minus 1. And some people, because this happens often, notice what we just did. Evaluating the function at -1 gave us -2, and doing this limit operation also gave us a -2. So many students make the mistake of thinking that limits, you just plug in the value. So many people think, oh, limit as x goes to -1 of f of x, just take -1 and plug it. That's very, very incorrect. It's coincidentally because you begin with very simple functions, and throughout this course we are going to deal with fairly simple functions. This is the result ends up being the same. But limit asks you to perform this process, you understand? Is to plug a series or a sequence of imitations to -1 in this case, and then figure out what's the tendency going to look like. Good? Here is another example, guys. Are you with me? So here is a function, and the function is defined to be x squared plus 1 if x is not equal to -1, and it's defined to be equal to 3 if x equals to -1. Now, please tell me what happens if I put -1 into the function. What am I going to get? Okay, I'm going to get 3. That's by definition. Now, what is going to happen if I push limit as x goes to -1? Okay, so that means that I am not plugging -1, I am plugging imitation. And since I'm not plugging -1, I'm not using this line here. I'm not using the lower row. I'm using this formula, x squared plus 1, agreed? Because this is the formula that works whenever x is not -1. So what happens? Here is just one table that might help me understand what happens. I plug in, when I say limit, I'm saying don't plug in -1, but plug ever better approximations to -1. So here is one possible sequence of approximations, minus 0.99, and I square it, I get this number, minus 0.999. I square it, I get this number. Here is an even better approximation. I square it, I get this number. You might guess that it will tend to 2, right? You might guess without even doing the table, because you think about it. If you square a number very similar to 2 and add 1 to it, you imagine you are going to get, a number very similar to -1 and square it and add 1 to it, you would imagine that you will get something very close to 2, even without doing this table. Do you agree? If 2 squared plus 1 gives me, if 1 squared plus 1 gives me 2, then something very similar to 1 or to -1 squared plus 1 will also give me something very similar to 2. So Ishmael, the reason I did this, I just try to illustrate, it's a very, very primitive function. There is no special purpose to it. I'm just trying to illustrate that plugging in a value is very different conceptually from taking the limit, okay? And again, what's the difference? Plug in the value -1, you just plug one value. When you take the limit, you don't plug one value. You plug infinitely many values, and they are striving to be -1. They're not -1, but they are imitations of -1. They're trying to be better and better copies of -1, but never perfect copies. And you plug them in, and you're trying to predict what is going to happen as I do it. And it's dynamically. I plug in better imitations. As I plug better imitations, I'm getting a better and better imitation of 2. You see what this is saying? Plug in better and better imitations of -1, you get better and better imitations of 2. Good? You see, this is not 2, but it's an imitation of 2. So eventually, if it were 1.99999, you cannot distinguish it from 2. Good? Now, this will be, I'm not sure if I'll present the rigorous definition of limit. We are not there. But I'm not even sure I'll present it for the Zoom classes. I do have a video lecture for that when I was teaching. So this is truly the better analogy of what you do. You're not really putting in a table. You're doing this, guys. Okay, so think of a function as a water cannon. Okay, imagine this water cannon can move around the x-axis. And you can do the following. You can shoot one particle at a time. So for example, if you say f of -1, that means you pick the one water molecule -1, you feed it to the cannon, and it shoots it somewhere, right? So in this case, or if this is the function that we were having over here, it will shoot the particle -1 to position 3 on the y-axis, okay? So you put -1, it will shoot somewhere up into position 3. Good? What is it that you are doing when you take limit? You put a cap, a lid on -1, so you're not going to put it in. and then you open up your valve, okay? And you push all the water inside of this valve into your function, and then it sprays out and you get a stain. You understand? The stain is going to contain possibly many values. You agree? Now, what you do is you close the valve. So now let's say the valve is closed and now it's around the green line. You see? The green parenthesis. So this is tighter around -1. Tighter squeeze around -1. The spray of the water will produce a stain that's tightly squeezed around 2. Squeeze it even more, the strain will be even tighter. So the limit, if you want to imagine a picture of what a limit is, imagine this water gun and imagine that you are closing in the valve. And as you close in the valve, the current, the water that is being sprayed, it's narrowing to a point. It becomes very sharp, right? See, this is the blue current, then it's the green current, then the red current, and the limit is that value around which the water cannon, the water is narrowed. You understand? And if you understand that, this will be later, from that it will be later possible to explain what limits are rigorous. So delta epsilon Cauchy, which is something you always do if you go into higher mathematics or anything where higher mathematics is involved, or physics as well, right? So if you're going to go beyond this class, and I mentioned, right, I'm hoping that you're convinced that there are some things that they are pretty interesting beyond this class. This is really nothing. Right? You covered calculus. It's nothing at all. It's just it might be even hard, but doesn't get you far. All right. So you understand this water gun analogy, I hope. So now let's talk about one-sided limits. Okay. So you see, notice in the approximations we did before, we could plug values. If I'm imitating C, I can plug values below C, or I can plug values above C. So what does it? So you write this as x going to C, and you put a minus on top, which means you plug values below C. So they are increasing, but are always less than C. And this means the values are decreasing, and they're always above C. Okay. Good. So here is, let's try to do the following exercise, guys, if you understand it, right? So here is a function. It's a piecewise function. It's defined by those formulas. I want you to figure out what is f of 3, what's the limit as x goes to 3 minus, and what's the limit as x goes to 3 plus. Go ahead, try to calculate. And write in your comments, for example, what A, and what's the answer, B, what's the answer, C, what's the answer. James, are you still around? James Loving Thomas.
Yeah, I'm still here. Sorry.
Great. Happy about. Now remember, guys, that if the limit exists, it has to be a number. X is just a meaningless expression. What is that? It means put something into the function, right? Put something into the function. What are you putting in? You are putting in B, you are putting numbers that are smaller than 3. When you say x goes to 3 minus, you're putting in numbers smaller than 3, but close to 3. And you try to predict what the answer is. Make sense? So when you say the answer in terms of x, there must be something incomplete. Well, any approximation is not no, finished. But Alexei, you are kind of right, except that it's not 5.99999, right? It's 5.99 forever, right? So the answer is 6 for B. Okay, cool. This is still cool. C is 9. Let's go through it again, guys. So f of 3, I see, okay, when x is equal to 3, I plug in 5, okay? Now, what happens if x is approaching to 3 minus? I'm plugging imitations of 3, but always smaller than 3. So notice I use the top expression, right? Because it says 2 times the value if the value is less than 3. So you see, x does not exist here, right? It's really just a placeholder. It says 2 times the value whenever the value is less than 3. So if that value is approaching to 3 from below, I use this formula. So I double it. And clearly, if I multiply 2 by a 3-like number, regardless of below or above, 2 by a 3-like number, this is going to be 6. Good, guys? 6. And then C, x goes to 3 plus. That's this line here. So what is that? That's 9, right? Because in this case, I plug 3 multiplied by a 3-like number. It's going to be 9. In particular, here I drew you the table. I plug 299, 299, 299, etc. You don't need to do the table. You can just kind of reason, right? If you multiply a number very similar to 3, you get a number very similar to 6. And this is the calculation that I would have done, right? So you plug, it's essentially you plug 3 minus, that's the fake 3. And what do you get? You get 2 times a number slightly smaller than 3. It's a number slightly smaller than 6, so the answer is 6. So you see, remember, Alexei, you wrote 5.9999. Why did you do that? Because the answer is really always smaller than 6. 2 times a number smaller than 3, always smaller than 6. So you write it. You can write it if you want to a 6 minus, but you end up with the answer 6. 6 minus doesn't matter much, okay? 6 minus means 6. It's tending to 6. You're predicting the current of the water current, whatever we call it, there will be narrowed around the 0.6 from below. So it's like the water droplets are hitting the y-axis below 6 there. Okay.
I think that wasn't enough. 9.
Right. And the other one, if you are you want to be precise about how the tendency is happening, it's really 9 plus. So it's 3 times 3 plus, right? And that means 3 multiplied by an impostor slightly bigger than 3. That would be 9 plus, but really we can just say 9. The only case that might matter in calculation is with 0, because 0 plus is positive, 0 minus is a negative number, or negative numbers. That are quite negative.
Wouldn't it be better to say it's approaching 9 or approaching
Well,
6?
when you say equal, that's just what we say is as x approaches 3 from above, the function expression, the evaluations approach 9. Okay?
It approaches 9, but then it equals 9.
Yes, we just write equal because approach is a long word, so you just say limit equals 9, which means the limit, the actual value that you're tending to. You see, the limit, we're already saying approaching. The limit of it is 9. That's your glass ceiling. Okay, 9 plus, so your glass ceiling is or maybe your glass floor in this case, right? It's whoop, you descend to 9. You're always above 9, but descend to 9. Good?
Yes, sir.
Yes, go ahead.
The whole concept of like the fake 2 or like the fake time of earlier was basically saying like it's smaller or bigger, but by such a small number, it might as well be considered the same thing.
Yes, exactly, right? So it's that's the idea. So it's slightly different so that you can carry the algebra, but it is essentially the same thing. It's really, if you think about it precisely, it's not one value, because it's really you have to be obsessively getting better and better approximations, continuously striving to get better approximations. Okay. So the fake number is really the idea of perfecting, right? Here is different. You're moving them closer and closer and closer, and you're trying to predict what happens. Okay.
Professor?
Yes, go ahead.
When we say that the limit is 6 or 9, it's not touching that per se, right?
Yes, well, the limit means that in terms of the water cannon analogy, it means that the particles, if you take all the particles together, they are gathering closer and closer around the value 9. In this case, if I take limit as 3 plus, I see I only take in the water gun, and I only squared water slightly above 3. Understand? And if I square this water slightly above 3, I always get all the droplets land above 9. That is 9 plus. It means they all land above 9. But as so it's from the right. I make the right wing of my interval smaller. The droplets, the highest the droplet can land is not very high above 9. You understand? Only slightly above 9. So the waters, you see, they're all focusing. So you actually, this is what I visualize. Droplets are hitting, and then they get closer and closer and closer to the floor, which is 9. You see? So the droplets are, it's wet, slightly over 9, but the stain is getting smaller and smaller and smaller. Good. Yes. What do you want to say, Alexei?
I have a question. So how far should the difference be between like 9 and like 9 like 8.999? How far is the difference for it to be not to be considered a full number?
Well, the point that's delta epsilon to be precise. What it means is that eventually, if you shrink the input current small enough, the observer, whoever the observer is, will not distinguish the result from 9. So somebody who is sharper can distinguish it for a longer amount of time. You understand? You have a detector. So you have a ruler, for example. On your ruler, if the ruler has centimeters, centimeter is the most amount of difference that you can tell apart. Okay. If you have millimeters on the ruler, then millimeters is the biggest distance you can tell apart. That's your resolution. So eventually, what this predicts, whoever is observing, whoever is making the measurements, eventually the error or the difference will be below the resolution that can be detected. Okay, so it's a very kind of it's a very engineering type of concept, you would say, right? So it's all about measurement. So then what do we say? We say that limit as x goes to c. Notice if I say x is approximating c, it means I can approximate from below and from above. So this limit will only exist if the approximations from below exist, if the approximations from above exist, and if the below and above approximations are the same. Understand? So for example, in here, the limit as x goes to 3 doesn't exist, because if you approach 3 from below, it's 6, and if you approach 3 from above, it's 9. So 9 is not 6, so the limit does not exist. Okay? I mean, you see what I'm saying, right? So, but only the sided limits exist. They are not equal, so the full limit doesn't exist. So you write it like this. You can write it's equal to the empty sign, or simply doesn't exist because of that. Good. And here, just we're not gonna. Maybe we'll do one graph here, and continue in the next class. One question, guys, before I speak about it, right? So you all graphed functions, right? You all drew pictures of functions when you were kids. And this represents, in a sense, a landscape. What's the dimension of this landscape? You see where this doll is walking. What's this dimension? It's an obscure question. I just wonder what you would say.
Sorry, what was the question again?
The question is, you see, so this is a landscape. This doll is walking on this landscape. This landscape is a graph of some function, right? The question is, what's the dimension of this landscape? So you say, for example, you live in a three-dimensional world. That's what you imagine, right? So you all seem to understand that. If you understand that, then what's the dimension here? So one person says 2D, 2D, 2D. Anybody? Well, two people say 2 dimensions. And what about the rest of you? Any other answer? Same. Any 2D? Come on, guys. There are a bunch of people. I want to see that you are here. It's good. It's a good way to show me that you are alive. Oh my God! Everybody see. Once a few people you said it. Everybody else like, my God, like rushing through. Let me tell you that not a single one of you is correct.
Is it x?
No, dimension. This is one-dimensional. You see what dimension? Dimension is why is the xy coordinate plane two-dimensional? To specify a point on the plane, you always need at least two numbers. Okay, so one-dimensional, you need one number. Two dimensions mean you have to specify at least 2 numbers to be able to locate a point in space. Three-dimensional, you need to specify at least 3 numbers to locate a point in space. Now, you look at this curve, it's like a bent ruler. You understand it? It's actually, the reason you think it's 2-dimensional is because it's a 1-dimensional space that curves or twists inside of a 2-dimensional one. Okay, so it's a twisted space, but really it's 1-dimensional, because if you are attached to the space, you can imagine it's just a bent ruler. A ruler is 1-dimensional because you only need one number to say where you're located. You understand? So in the car, we had a ruler for the position of the car. We only needed 1 number. So if I say 5, you know where the car is located. 5 was the traffic light. Okay. So here you can imagine it's just a number line that was bent, and you can imagine the markings on this number line. It's 1-dimensional. This is not important for this class, but it will be, if you go on, important when you study manifolds, for example. Right? Maybe some of you will do it very soon. It's pretty impressive how quickly people move from calculus 1 to everything and then graduating and who knows what. Well, so today's lecture is over. I will stop the recording, and you're welcome to stay with me and ask me questions, or just talk if you're interested in talking. What I'm truly interested in is how many of you watched Zuharit Bhakti.